In the next series of slides, we're going to be looking at some green chemistry metrics and how can we assess how good, how environmentally friendly, how green a reaction is. The traditional way of measuring how good a reaction is by looking at percentage yield. And percentage yield is how much product have you formed divided by how much product you were expecting to form from that quantity of reagents. So if you have a very simple reaction, A plus B, that gives you C plus D. And let's say that you're interested in C. You will work out, okay, how many moles of A and how many moles of B do I have? And how many moles of C would I expect to get from that reaction? So that reaction I've written there is the ratio is 1 to 1. So if I have 1 mole of A, that will give me 1 mole of C. Or if I have 1 mole of A and 1 mole of B, that will give me 1 mole of C. And if you multiply the molecular mass, that will tell you, oh, that's how much C I was expecting. But that's never the case. In a chemical reaction, the reagents not always react completely, and so you tend to have to add some extra reagent because the reaction, it just doesn't go to completion. And then when you start processing the product, let's say you have to filter it, or maybe you have to dry it, or maybe you have to distill it, all that means that you are losing product from one step to the other. So when you end up with your product already in a container, oh, I've got my product C and this is over, you have lost a lot of product along the way, sometimes right at the beginning because the reagents haven't just reacted completely. So the actual mass of product, how much of the chemical you actually get, is never as much as you expected. So an ideal percentage yield would be 100%. So you have as much product as you were expecting to have by the amount of reagents you have used. And then what would be a good synthesis? Well, that's a matter of opinion, but you can see, oh, like 90% of my chemicals, or 95%, or 70%, whatever number you can think of. If you pick, let's say 95%, 95% of the mass I was expecting to make it into, of product I was expecting, I actually got. And that's a traditional way of assessing how good a reaction is. The higher the yield, the more we are aiming for 100%, but the higher the yield, the better the reaction is. Atom economy looks at the theoretical efficiency of a reaction in a slightly different way. It looks at what is the mass of the product divided by the mass of the reagent? Because ideally, you would want, and the molecular mass, I don't mean the actual mass of it, no, I mean the molecular mass of the product divided by the molecular mass of all the reagents. So how many of those atoms of reagents actually make it into the product? In this case, how many atoms of A and B actually make it into C? And how many actually make it into byproducts, D, that we are not aiming for? And that's what atom economy tells you. What's the molecular mass of the product divided by molecular mass of the reagents? Times 100 because it's a percentage. How many of the atoms that we have in the reagents actually make it into the product? It does not account for what solvents you might use. It doesn't account that those two metrics individually have limitations. The percentage yield doesn't account for actually how many atoms of the reagents go into the product. And the atom economy, it doesn't account for actually how much is the yield of a reaction, how much you have lost in the processing the product, filtering, distilling, separating the product from leftover reagents, etc. So a way of combining those two aspects, how much I actually get from a reaction and how efficient it is in terms of how many atoms of the reagents go into the product, can be combined on something called atom efficiency, which is the percentage yield divided by the percentage atom economy. And it kind of gives you, it then includes both aspects of that, of those two metrics. You might also want to assess how green, how good, how environmentally friendly, how sustainable your reaction is by looking at something called effective mass yield. And that is the amount of product you get in kilograms or in any units of weight divided by the amount of hazardous reagents you use times 100. So, okay, you have obtained a large amount of product, but you also have used a huge amount of hazardous reagents. That is not a very effective mass yield, because you are having to deal with loads of hazardous reagents to produce that product. This doesn't tell you it doesn't look at the stoichiometry of the reaction. It just tells you, okay, you have started with this many kilograms of reagents. Of those reagents, these ones are considered hazardous, and this is how many kilos you have used of them, and this is how many kilos of products you have produced. And it is, I suppose, it is subjective to decide what is hazardous reagent. I mean, some of them will be clearly hazardous because they are, extremely hazardous. But most of them are what is hazardous in the context of chemistry, when most of the chemicals we use when we are in a lab have a certain amount of hazard associated. That's why we wear safety glasses and lab coats and use gloves, because we are trying to minimize that hazard. So how do you decide what is benign, and how do you decide, oh, this is what I'm going to consider a hazardous reagent? And there isn't a sort of accepted standard. Another thing you might want to look at is the E factor. And it's a simple metric that kind of tells you with a number how green a reaction is. And it's the amount of waste you produce, and it doesn't have the judgmental of the previous one, which is, oh, what is hazard, what is not hazard. No. This one is the total waste you produce divided by the amount of product you produce. Ideally, you would want that to be 0, because ideally you would want not to have any waste and have all products, so that would give you 0. And the lower the E factor is, the more, ideally, the more environmentally friendly that reaction, more green that reaction can be considered. And it might be interesting to know that in the different chemical sectors, things that, for example, you might not think are particularly environmentally friendly, actually, in terms of their E factor, they are much better than others that might not come across as particularly not environmentally friendly, not particularly green. For example, if you look at the chemical industry, the E factor of the pharmaceutical sector can be quite bad, between 25 and 100. And that is because in many cases, they are generating very valuable products, and I mean economically valuable products, perhaps even with the patents, things that, products that are going to be sold at a very high price, and they're also very difficult to make. They are pushing the boundaries of science, of medical research here. So some of the synthesis of the pharmaceutical sector can be actually really wasteful, because the cost of that, disposing of that waste, is absorbed by the price of the product. Well, for example, if you look in, for example, of the oil refining industry, has a tiny E factor, because although you might not consider as particularly environmentally friendly, they work with a very tight profit margin. The same with bulk and fine chemicals. Bulk chemicals will be the ones that you would use in a factory. Fine chemicals are the type of chemicals we use in the labs when we're doing practicals. They actually work with much narrower profit margins, so they cannot afford to generate that amount of waste. So as you can see, there are several ways you can measure how green, how environmentally friendly, how sustainable a reaction or a chemical process is. And they all have their pros and cons. So a combination of all of them is useful to actually assess how green a reaction is. In the next few slides, I'm going to be concentrating one of them, which is atom economy.